You know, language is one of those amazing human things we just take for granted. But think about your day. You're constantly typing questions into a search engine, telling your phone to set an alarm, maybe even using a translation app. We are talking to our tech all the time. But have you ever stopped to wonder how a machine, a piece of code and silicon, actually gets what our words mean? I mean, how does it go from just seeing letters on a screen to actually understanding them? That's the huge challenge we're going to unpack right now. The answer to that question lies in a fascinating field of AI called natural language processing, or NLP for short. And really, it's all about one big goal: teaching computers our most human skill of all, language. Now, you can kind of think of NLP as having two main jobs. First, there's natural language understanding, NLU. That's the reading part, like a spam filter, figuring out what's junk mail. Then you've got natural language generation, NLG. That's the writing part, like when an AI whips up a summary of a long article for you. So for both of those jobs, understanding and generating, the absolute key is getting a handle on what words actually mean. And this is where it gets really, really tricky. Because words themselves, they don't have any meaning built in. They're just symbols. We're the ones who give them all their meaning. Just take a simple sentence like, "Meet me at the bank." Without any context, how is a computer supposed to know if I'm talking about a riverbank or a money bank? It's totally lost. And it's not just definitions. What about sarcasm? If my fridge is broken and I say, "Oh yeah, this fridge is great," you know exactly what I mean. A computer? Not so much. It turns out context is everything. So if the words themselves don't hold the secret, where can a machine possibly look for clues to their meaning? Well, one of the first ideas was pretty straightforward. Maybe we can just look at how the words are built. This approach is called morphology, basically looking at a word's parts. And for some words, it actually works pretty well. If you know the root word swim, it's not a huge leap to figure out what swimming or swimmer means. Same thing for drink becoming drinking or drinker. You can just build a set of rules. But yeah, that idea falls apart really fast. Knowing what a van is gives you exactly zero help in understanding a vandal. And look at cat and car. They're almost the same exact letters, but their meanings are in completely different universes. So that simple rule-based system, it's just not going to cut it. This is when a huge breakthrough came, not from computer science, but from linguistics. It's summed up perfectly in this quote from John Firth: "You shall know a word by the company it keeps." This idea, called distributional semantics, was a total game changer. It says a word's meaning isn't in the word, it's defined by the other words that tend to show up around it. Okay, that's a brilliant, beautiful insight. But computers don't really do beautiful insights. They do math. So the next critical step was to figure out how to translate this whole idea from the world of words into the world of numbers. One of the first ways we did this was with something called count vectors, and it's a pretty simple idea. It's basically just a tally. You count how many times a word shows up in the same text as other common words. The thinking goes, the more their company overlaps, the more similar their meaning is probably going to be. And let's see if that actually works. We took the Wikipedia articles for cat, Felidae, that's the scientific name for the cat family, and car. After we got rid of all the common filler words, the results were crystal clear. The words hanging out with cat and Felidae are almost identical. The words with car, a totally different group. So hey, this method, it really works. But there's a really big problem here. To do this for all of language, you'd have to create a massive, basically unmanageable list of every single word and every other word it's ever appeared next to. For the entire internet, it's just not practical. It's an impossible amount of data. And that brings us to the modern way of doing things. Instead of this brute force counting, we got smarter. We trained the machine to learn a compact, efficient representation of a word's meaning all on its own. It learns to encode the important info about a word and then decode it to make predictions. A really great way to think about this training is like a giant game of fill in the blank. Seriously. If you give a model the sentence, "I'm kind of hungry. I think I'd like some chocolate blank," its job is to guess the missing word. It'll learn pretty fast that cake or milk are good guesses, but potatoes is a really bad one. By doing this millions of times, it starts to figure out which words belong together. Now for more complex sentences, it gets tougher. The model has to do more than just look at the last word. It has to actually remember key details from earlier in the sentence. So in a long sentence about your friend Diana, who loves physics, the model needs to remember her name from 27 words ago to fill in the blank correctly later on. It needs a memory. The tech that gives it this memory is a special kind of AI called a recurrent neural network, or an RNN. The way it works is, it reads a sentence one word at a time. And that little loop you see there, that allows it to keep a running summary of what it's already seen, building up its understanding of the sentence's structure and meaning as it goes. So what does this understanding actually look like inside the machine? It's not the letters C, A, T. Instead, every single word is represented by a unique list of numbers. And that list of numbers is called a word vector. You can think of it as the machine's own mathematical fingerprint for that word's meaning. Okay, so we've been through a lot of theory, counting words, playing fill in the blank, neural networks. So what's the big payoff? Well, the payoff is that we get machines that have a real usable grasp on what our language actually means. And that has changed everything. And you can actually see the results of all that training. When we visualize these word vectors, you can see that words with similar meanings, like chocolate, cocoa, and candy, they all cluster together mathematically. Meanwhile, physics is way off in a completely different part of this space. The model learned what words mean just by seeing what company they keep. And that brings us right back to where we started, to the real world. This whole incredible process is the engine running under the hood of all the technology we use every single day, from translation apps to voice assistants like Siri and Alexa, all the way to controlling robots with just our words. Which leaves us with a final, fascinating question to chew on. The AI researcher Professor Ray Mooney once said that we'll never fit the whole meaning of a sentence into a single vector. And, he might be right, but as we get closer and closer, we keep unlocking these unbelievable new ways for humans and machines to communicate, which really makes you wonder, what are the limits?